Education course. We begin with the Dr. Roshchenko, continuing with the topic of dosimetry of ionizing radiation.
Good afternoon. Today we have lecture number 2. We continue with dosimetry. Today we will cover some fundamental aspects of dosimetry. We are waiting for them. Oh, it's me. Okay. I'm switching slides. Yeah, that's fine. So today we will cover those concepts, important properties of ionizing radiation, and basic arithmetic quantities. So starting from that radiation protection and radiation safety are scientific disciplines aimed at recognizing, assessing, and controlling the risks associated with the use of source of ionizing radiation. The objective of protection is to prevent deterministic effects from occurring in individuals by maintaining doses below an appropriate threshold, and to ensure that all reasonable steps are taken to reduce the occurrence of stochastic effects in the population now and in the future. The goal of safety is to ensure that individuals, society, and the environment are protected from harm by establishing and maintaining effective defenses against radiological hazards associated with sources. Thus, the radiological field, the radiological triad, the act of ensuring safety when using sources of ionizing radiation includes identification of the sources of radiation hazard, determination of the magnitude of the impact of the source on a person, and assessment of the risk of developing of radiation effects as a result of exposure to a source of radiation risk. The transfer of radiation energy to matter is a starting point for the development of biological effects in humans, animals, plants, and microorganisms. In all living organisms. The concept of the dose of ionizing radiation is that the effect of radiation are associated with the energy absorbed during ionization and excitation of atoms and molecules in the unit mass of tissue, and with the quality of radiation, which depends on the microscopic spatial distribution of energy transferred by radiation to matter. The exposure to radiation may also depend on other factors, such as the rate of energy absorption, the degree of oxygen supply to the irradiated tissue, and other factors that affect the radiosensitivity of the irradiated tissue. Radiation protection and safety includes a system of criteria, methods, and means aimed at ensuring human safety when using sources of ionizing radiation. An important task of radiation protection is to assess the consequences of human exposure in terms of the risk of developing severe radiogenic diseases, the effects of radiation. In solving this problem, dosimetry of ionizing radiation plays a major role designed to characterize the conditions of exposure in terms of physical quantities needed for use in risk assessment. The physical processes underlying the phenomenon of radioactivity and the interaction of radiation with the matter are of a probabilistic nature. Their characteristics are discrete values of random variables, the number of nuclear transformations per unit time, the energy of the emitted particle, the number of particle interactions in the medium, etc. In most cases, when the stochastics of processes can be neglected, the mathematical description of this phenomenon uses continuous functions that characterize dependencies that relate the expected values of the corresponding random variables. This general approach allows to use the differentiation and integration operators in determining radiometric and dosimetric quantities. The average value of a result of observation and the mathematical expectation of a random variable are not equal. The average value of the measurement result lies in a certain neighborhood of the mathematical expectation, the size of which is determined by the variance of the mean. To achieve their goals, radiation protection and safety rely on a system of quantities that can be conditionally divided into radiometric quantities used to characterize sources and fields of ionizing radiation. And the second part, dosimetric quantities, used to characterize the effects of radiation on humans. They, in turn, are divided into two large groups, which include basic dosimetric quantities and equidosimetric quantities. Basic physical quantities are considered in this lecture. Equidosimetric quantities will be discussed in lecture number 4. So the activity of radioactive source, A or P, reflects the average rate of nuclear transformations occurring in it at a given time t. Its value is proportional to the number of radioactive nuclei n of t located in the source at time t. And activity is equal to the production of decay constant lambda to the amount of nuclei n of t. As I said, lambda is decay constant, coefficient of proportionality here, and f dimension number of decays per second, 1 second. The decay constant is equal to the probability of the nucleus decaying within 1 second and is related to the half-life by the ratio to natural logarithm of 2. We saw this equation in the previous lecture and in lecture of other professors. So the value of the half-life is the main characteristic of the radionuclide. Thus, the activity of a given amount of radionuclide of a substance containing only stable nuclei is equal to 0, since the half-life of such nuclei is assumed to be infinitely long. Decay is a random process that obeys an exponential distribution law. The law of radioactive decay, which defines n of t as a function of time, can be written as the expression for exponential decay minus lambda t, where n0 is the initial number of radioactive nuclei in the source. The source activity decreases with time as a result of the radioactive decay of unstable nuclei. For example, if there is a source containing 10 to 12 becquerels of iodine 1D1 is applied 8 days. In a week, his activity will become 5.5, 10 to 11. In a month, it will 7.5 to 10 to 10. And in 1 year, it will be something 10 to minus 2 becquerels. The radioactive source is a material containing a radionuclide. A quantitative measure of the radioactivity of a source is activity, A, which is defined as the ratio of the average number of spontaneous transformations of nuclei from a given energy and state over a time interval dt to a given time interval. Activity unit is 1 over second, which has a special name, becquerel, named after known physicist. Open the radioactivity. In a source is activity of 1 becquerel, an average of 1 nuclear transformation per second occurs. The unit of activity used to be 1 curie. Best. 1 curie is 3.7 to 10 power 10 becquerels. There are units named after the scientists Becquerel and Curie. According to the rules for the literature for naming physical quantities, the units of such quantities are given with the capital letters. See this. The presence of a radionuclide in the source can be determined as follows. So the volumetric activity is activity divided by volume and denoted as A with index B. Also, mass activity is actually activity divided by mass of the radionuclide or surface. In the nature, radioactive materials are ubiquitous. We are exposed to them every day. Material radiation has been accompanying us. Natural radiation has been accompanying us since the birth of the universe in the Big Bang. Natural radionuclides are found in our bodies, in the food that we eat, in the places we work and live, in the land we live on, and in the food we use. Any natural substance around us contains natural radionuclides. These radionuclides determine the background of natural radiation and its daily impact. The most significant among them are lithium, carbon-14, potassium-40, thorium-232, and some uraniums, uranium-234, 35, and 38. The main contribution to the radiation background is made by radionuclides resulting from the decay of existing natural isotopes of uranium, uranium-8 and uranium-5, and uranium-4, and also from thorium. The descendants of radon-222 and radon, radon-220. The element potassium, a common component of the human body, exists in 3 isotopic forms: potassium-39, potassium-40, and potassium-41. Two isotopes, potassium-39 and 41, are stable isotopes, and together make up 99.99% of potassium. Existing only in small concentrations, unlike other potassium isotopes. Potassium-40 emits beta-minus particles and gamma radiation, and therefore is a natural radioisotope of potassium. the relative ratio of the three isotopes of potassium is the constant value, regardless of the source. Therefore, since the adult human body contains 150 to 200 grams of potassium, 15 to 20 milligrams of it will always exist in the form of carbon-14 radioisotope. Since the content of natural potassium in the human body is a constant value, the content of potassium 40 is also a constant value, regardless of the degree of the intake with food. Another source of natural radioactivity is the air debris bombarded by neutron radiation from the sun and from the space, the weak radiation. Atmospheric nitrogen, as a result of a nuclear reaction of neutron capture with subsequent emission of a proton, turns into a radioisotope of carbon-14. You can see amounts of radioactivity which can be emitted in standard product like coffee or phosphate fertilizer. Ionizing radiation is called the interaction of which with the matter leads to the ionizing of atoms and nucleus, because the appearance of ions of different signs in the irradiated substance. Propagating in the medium the flow of particles or gamma quanta creates a field of ionizing radiation. If this is no interaction, if there is no interaction of radiation with the medium, radiation propagates in vacuum, or it is small when photons propagate in air. Then the trajectories of particles and quanta in the medium can be represented by straight lines. The interaction of radiation with matter leads to a change in the radiation field, to the scattering of radiation and its absorption, as shown on the slide. These changes depend on the probability of radiation interaction with matter, radiation cross section. For example, photons pass quite freely through a layer of water, a few centimeters thick, but will be scattered and absorbed by lead to a large extent. Neutrons, on the contrary, scatter significantly when interacting with water because of hydrogen and interaction with it, and not interacting with lead. Interact, but not big amount, like in the case of hydrogen. The field of ionizing radiation is characterized by a number of parameters: type of radiation, direction of radiation propagation, radiation energy, and radiation lines. For the purpose of dosimetry, radiation is divided into two groups. The first group includes radiation consisting of charged particles, electrons, protons, alpha particles, etc., which directly ionize atoms and molecules when passing through matter. The second group includes neutrons and photons, which do not directly ionize atoms and molecules of matter. Interacting with matter, these radiations gives rise to secondary charged particles, transferring part of this energy to them. The interaction of these secondary particles with matter leads to the ionization. Thus, there are two types of ionizing radiation: directly ionizing and indirectly ionizing. The basic unit used to describe the energy of a particle or photon is the electron volt. discussed yesterday. Most important quantitative characteristic of the radiation field is the lines of particles or photons. This value is determined as follows. Let's place in the radiation field an absolutely transparent test sphere with a cross-sectional area equal to ds. And let's calculate the average value of the number of particles or photons that will cross the surface and get inside the sphere. Fluence of particles or photons is determined as a ratio of the average number of particles that have entered the sphere to the cross-sectional area of the sphere, ds. It's shown in this slide. Usually, the word particle is replaced by the name of a certain elementary particle. For example, neutron, pions. The units for fluence of pions is 1/square centimeter. Fluence is an integral characteristic of the ionizing radiation field. Its value is directly related to the time during which the number of particles penetrating into the test sphere is determined. To describe the change in the radiation field over time, the particle or photon flux density is used, which is defined as a ratio of the lines increment df over a certain period of time dt to the duration of this period, shown on the right side of this slide, at the bottom. The units of particle or photon flux density is 1 divided by second and squared centimeter. The sphere on the slide represents the location of a point in the substance question. It is surrounded by a volume of radiation absorbing materials. The sphere and its ions are located in the primary radiation field of indirect ionizing particles, these arrows. Primary radiation interacts with matter and transfers its energy to secondary directly ionizing particles, solid arrows. The fluence of the particle is the number of particles that have crossed the elementary sphere in any direction, divided by cross-sectional area of the sphere. The radiation fluence is the time interval of the particles flux density. If the flux density of particles or quantum doesn't change with time, then there is a linear dependence of the fluence on the time of exposure of the radiation field to the object. Thus, the fluence of radiation passing through the human body due to the impact of any source is a product of the flux density of radiation particles and the exposure time. So here we can introduce the first rule. Any reduction in time spent in the radiation field will reduce the total dose received. This obvious. Radiation from a source point propagates through the medium like light. If the distance from the source is much greater than its dimensions, the flux density of the radiation particles changes in accordance with the R-squared law. This R-squared law is the inverse proportionality of the flux density of radiation particles with respect to the square of the distance from the source point. It is easy to show mathematically that the fluence power varies inversely with the square of its distance from the source. Doubling the distance from the radiation source, reducing the radiation fluence power or flux density. And the corresponding dose rate by a factor of 4. Increasing the distance by 3 times reduces the dose rate by 9 times, etc. So another rule we can introduce here: the greater the distance from the source, the lower the flux density of radiation particles. In the formula on the slide, you can see here, A is the actual activity of the radiative source in becquerels. Y is index R. The external yield, probability of exit from an atom of particles or photons of type R in one nuclear transformation in the source. And R is the distance from the source in centimeters. And small p is index R, the flux density of R-type radiation particles at a distance R from a source. Uncharged particles and photons can cause ionization only indirect through secondary radiation. The interaction of uncharged particles and photons with matter is a random process. Interactions are rare, but in any interaction, a particle can lose a significant amount of energy. Quite often, an indirectly ionizing particle loses all its energy in a single interaction and disappears. For example, a neutron is absorbed by the nucleus, and a photon is converted actually into the electron-positron pair, or transfers all the energy to an electron as a result of the photoelectric effect. The probability of interaction of an individual ionized particle directly ionizing particle with a substance can be significantly characterized quantitatively in terms of the mean free path. The higher the probability of interaction, the shorter the free path of the particle between successive interactions, and more radiation energy is transferred to the substance. The mean free path is the average distance that a particle or photon travels between a specific type of interaction in a given medium. The mean free path can be defined for all interactions, this total mean free path, or for individual type of interaction, such as scattering, capture, or ionization. The value of the mean free path depends on the properties of the substance and on the type of radiation. Its value for some materials and radiations is presented below. Here we see that, for example, photons from cobalt source, cobalt 60, it is gamma quantum that can fly through water 16 centimeters and in lead only 1.6 centimeters. And if you take fission neutrons, here the opposite picture. In water it's only 8 centimeters, in the lead it travels 14 centimeters. This data shows that the probability of interaction with matter in the human body is higher for neutrons than for photons. The human body effectively scatters neutrons and distorts the field of neutron radiation. Therefore, exposure of person to neutrons is always uneven, in contrast to exposure to photons. The interaction of photons with matter is a random process. So the passage of primary radiation to the absorber layers obeys the exponential law. When a parallel photon beam penetrates to an absorber layer or thickness T, this attenuation factor U the particle flux density on unscattered radiation after the absorber layer will depend on its thickness, as shown on the slide, and as discussed in the previous lecture with a problem. Burns of unscattered radiation of a point at the topic source at some point in space is determined by several factors. See the slide. In most cases, the contribution of scattered radiation can be neglected. In this case, the radiation burns of a point at the topic source at the selected point in space depends on the above factors, as shown on the slide below. The first factor is equal to the number of particles with energy E, this R capital, that were emitted by the source during the exposure time. It illustrates the principle of time protection, which is that the shorter the exposure time, the lower the radiation dose. The second factor reflects the law of geometric attenuation of the primary radiation. It illustrates the principle of protection by distance, which is that the further the irradiated object from the source, the lower the dose of radiation. The third one factor reflects the law of exponential attenuation of primary radiation, and it illustrates the principle of shielding protection, which is that the thicker the absorber layer that shields the source, the lower the radiation dose. The Planck's estimate obtained, the Planck's estimate obtained by the above method can serve as the first step in a quick, also not very accurate calculation of the dose of an external photon radiation. At the second stage, the Planck's assessment is used to assess the doses of exposure to organs and tissues of the human body. So on this slide, again, A is activity, Y is index R capital is the external field of particles, external yield of particles or photons, type R in one nuclear transformation in this source. P is time, R is distance, and P is thickness of absorber. And mu is the primary radiation attenuation factor in the absorber. Units 1/centimeter. Presence of ionized radiation for a substance leads to the interaction of particles and photons with atoms, during which the radiation energy is transferred to the substance. The result of energy transfer is considered from two sides. With regard to the radiation, its field changes due to its interaction with matter. As applied to a matter, energy is absorbed and its state changes due to the energy transfer by radiation. Thus, it is advisable to consider two characteristics or two aspects of the transfer of radiation energy to matter. The first is kerma, reflects the radiation energy absorbed by matter and characterizes the radiation field by its loss of energy due to interaction with matter. Kerma is a protein, kinetic energy released in matter. And the second one is absorbed dose, reflects the radiation energy transferred to a limited volume of matter and characterizes the substance in terms of energy absorption due to the interaction of radiation with matter. The exposure dose was the first dosimetric quantity used in the metrology. Only the photon radiation field in air. This value was approved by the International Commission on Radiological Protection in 1928, when only one type of strongly penetrating radiation was known, photon radiation. During this period of time, the biological effects of ionizing radiation were not well understood. And the goal of radiological protection was to limit only the intensity of photon radiation. The exposure dose is proportional to the photon radiation energy expended on the ionization of air molecules, and is equal to the ratio of the average value of the total charge of all ions of the same sign created by the air. In the air, and when all the electrons and positrons released by photons in the elementary volume dm completely stopped in the air. So the mass of this volume m. The old unit of exposure dose is the Röntgen main chapter on physicist. The CSI unit for exposure dose is coulomb per kilogram. Exposure dose is directly related to the fluence of photon radiation. In radiation monitoring, it is replaced by the air thermometer later in this lecture. So this cube represents the elementary volume of air of interest. It is surrounded by a volume of air that scatters the radiation. The elementary volume and its environment are placed in the field of primary photon radiation. So this arrows here. Primary radiation interacts with air and transfers its energy to secondary directly ionizing particles, which is shown by solid arrows. This radiation, charged particles, ionizes matter inside the volume and surround air. It causes the ionizing produced by photons in the air. The general basis for characterizing the effect of various types of radiation on matter is a linear energy transfer, LET. This value characterizes how the radiation energy is transferred to the substance. Total linear energy transfer, L, is the energy transferred by ionizing particle to matter per unit length of its trajectory. So, as a rule, the LET of radiation in radiation safety means the complete transfer of energy to liquid water, intensity 1 gram per cubic. This value is used to evaluate the radiation quality. The unit of measurement of LET is kiloelectron volt per micrometer. The LET value varies for a wide range and is largely determined by the particle velocity. The slide shows that the higher the LET of a charged particle, the smaller its free path between successive interactions with matter, and the more ionized atoms and molecules per unit Planck length of such a particle. Here we can see here, for example, alpha particle and electron. Just compare amount of ionization. The quantity that reflects the interaction of the field with indirectly ionizing radiation with matter is Kerman. Abbreviation with abbreviation of the term kinetic energy released in material. It is defined as a ratio of the average value of the sum of the initial kinetic energies of all charged ionizing particles, electrons, positrons, protons, alpha particles, etc., formed under the action of ionizing radiation in an elementary volume of a substance, to the mass of the m of this substance in this volume. The units for Kerma is joules per kilogram, and have special name gray. Air Kerma is the Kerma value for air, which characterizes the undisturbed radiation field. At the same point of the photon radiation field, the value of the air Kerma is practically proportional to the value of the exposure dose. If the exposure dose at point the photon radiation field is 100 again, the air Kerma at the same point is approximately 8.7 milligray. This relation is valid for a wide range of photon energies. So we can use it to calculate something. The cube on the slide represents the elementary volume, much just like the same like in previous time. It appears several more times. So it's surrounded by a volume of a matter that scatters radiation. The elementary volume and its environment are placed in the field of primary indirect ionizing radiation, shown by dashed lines. Primary radiation interacts with matter and transfers its energy to secondary directly ionizing particles, shown by solid lines. Energy of this radiation charged particles appears inside the elementary volume solid cubes and represents the energy of charged particles released in matter by uncharged particles or photons. The energy transferred by ionizing radiation to the elementary volume of a substance is equal to the difference between the sum of the energies of all directly and indirectly ionizing particles that entered the volume and the sum of the energies of all those particles that left, minus or plus the energy equivalent to the increase in other case in mass rest of mass, which took place in nuclear reactions with elementary particles inside the volume, like proton and electron annihilation. The cube on the slide represents the elementary volume again. All the other stuff is the same. Solid arrows and pressure elements. And then the absorbed dose is the value that characterizes the effect of ionizing radiation on a substance and reflects the change in the state of an elementary volume of a substance under the action of radiation. It is equal to the ratio of the average value of the energy transferred by ionizing radiation to a substance in elementary volume to the mass dm of the substance in this volume. So those units joules per kilogram as well as special names gray. Previously rad was used. 1 rad is 0.01 gray 1%. So the cube on this slide is the same notations, there's the same notations. Elementary volume of the substance and pressure is surrounded by volume of matter that scatters radiation and scatters. come to some conclusion. From the point of view of assessing the biological effect, we are interested in the ionizing ability of radiation. Therefore, in the characteristic of the transfer of radiation energy to a substance, only that part of energy lost by radiation which went to ionizing, which went to ionization and excitation of atoms and molecules is considered. So basic dosimetric quantities are the measure of the interaction of ionizing radiation with matter and the transfer of radiation energy to matter. The properties of the basic dosimetric quantities are determined only by the physical processes of the interaction of radiation with atoms and molecules of the medium, which are well studied. So these quantities remain unchanged for a long period of time. That's actually all for this lecture. Any questions? Maybe online? Thank you.